done, or like compositional studies can be done. But for this practical or this session, we will be creating a new data file. So let me just select new. And in this section, we will select the star simulator because stars we will be using. And I will be using this lab as working unit because I'm going to show how to simulate a core flood, which is done in your labs or in any lab, and to basically test the test the enhanced oil recovery capacity or water flooding capacity using only core, not the entire reservoir, but only core. And then it is used for the several other purposes. The data which is or the result which is found by these core flood experiment. So that's why I will select this lab, and the porosity will be the same as single porosity. Or we can also select SI because the information maybe which we know is mostly in terms of the tutorial which I am going to show. I have most of the data in SI unit, so only SI I will be selecting. The start date for the data set which I have is 1st of January 2012. I will click OK, and again I will click OK. Now, because now, like in previous case, you have seen that we had a BNA file or a contour file which was used for creating the simulation space or creating the grids. But mostly in case of code flooding, we do not have that information, or that information is not required. And in case of core flooding, we mostly use a one-dimensional flow. And one dimensional flow, if I can tell you, like if I will select on this arrow button in front of reservoir and click go to create grid and select Cartesian. So one dimensional, you all know, it will have only the grids in one direction. So I will select, like in I direction, let's say I have 11, but in case of J direction, I will only select that the grids are to be divided into one part only. So the entire grid or the entire model that be made will have 11 sections or 11 grids in I direction, but in J and K direction, it will be only one. And the dimensions for this is which, and using the data which I have for it is 0.009075 space 9 into 0.01875 and again 0.009075. This I think you all know that if I give the data in this format, the first grid will be of 0.009075 meter because I selected the unit as SI. Then next 9 grids will be of this dimension, that is 0.01875, and the last will be again 0.009075 meter. So this is basically because I will be the last of the 2 grids are much smaller and the other 9 grids are a little bigger, because the last and the first grid will be used as a injector point and the production point. So that's why I have selected two small grids on the extreme ends of this core, and the other grids are a bit bigger. In the J direction, it is 0.033375 meter, and then I can click on OK. So this will be the grid that will be formed, and it is, as you can see, only it is in one direction. Now I will be specifying the rock properties for this, and I can double click on array properties and I will get to this window. And for this, I will be selecting the grid top for the layer 1 as 1000. The grid thickness for the whole grid will be 0.00333 3375. Porosity is taken as 0.2494. Permeability in IJK, all the directions is 2591 millidarcy, that is around 2.5 darcies. So because this is a one-dimensional model, whatever value I give in the J and K direction, that will not have much effect, or you can say it will not have any effect on the any result that will be formed. But we have to give some value because we cannot leave it blank, and because the simulator also does not know that we are making a 1D model. So we have to give these two values even if the flow will not be in the J and K direction. And other, now this was the initial or the minimum requirement. Apart from this, I will also specify the pressure and temperature uh, for this entire model, because I have those data. So to go to, I can either go click on the arrow button and go to the pressure, or I can also go to pressure using this option where the list of all the properties are given. So the pressure is for the whole grid is 100 kilopascal, and also the temperature I will be specifying. The temperature is 31 centigrade. Click on OK, and again I will click on OK. So now I have entered all the array properties. It is just showing one warning for the pressure, but that will be rectified when I will give the further values. So let's save this data set at this point. Now, sometimes like you will see that we are not getting the save option, and that is because we are not in the probe mode. And to go to the probe mode, we have to select this small button which enables the probe mode for this model. I will select this, and then you can see that I have the option of saving this model. So let's save this as practical 2. Click on OK, and have been saved. So, so this this we have made a reservoir model, or you can say a model for a very small core that is having a dimensions of around, if you will calculate, I think it will be around 19 or 18 centimeter, and then this is like the total dimensions. So this is the 3D view, and you can click on this button and rotate the entire grid and see how the models look like. Okay, so after this, the next important thing is that we have to add the fluids, and like we have entered the rock properties. Now we have to enter the fluid properties. What are the different fluids or the reservoir fluids that are present? So for that, we will go to the component section, and you can double click on this. No, you can go to this arrow button and click on this add or edit components option. Or if you have a Blackwell model which you have made in you can say using the stars, you can also import that Blackwell PVT model. Other options which you can see is that you can import a WinProp generated model, which if you have a compositional data, compositional data of the crude oil, you can use that WinProp, import WinProp generated model, or you can also create a new model using the WinProp, for which the tutorial of how to use the WinProp will be given in your later classes. And for this, I will be clicking on this add or edit component. And at present, you can see this is entire blank, and we have to add few components that are present in the reservoir. So for that, I'll click on this add or edit a component. Sorry. So this window comes where you can input the uh, values or the properties of the any component. So the CMG also have a library from which you can select what types of fluids are there. Like if we know that there is let's say methane or ethane, we can simply click on that and that can be added as a component in this model. So at first I have to add water phase. So I will be clicking on H2O and it is added and it is already defined that this is this H2O component is in aqueous phase. And for the critical pressure and temperature, if I know a specific value, I can enter that value or I can also enter zero. And if I enter zero in these three options, what the reservoir will do, it will take the default values from its library. So as I've already entered that I can take all the value from the library, so I will be entering like for H2O it can also take the default value but for the dead oil which we have added, we have to enter the I guess we have to enter the mass density because that's what we have, and it is 869.2. Now mass density is the unit is kg per meter cube, and that is like that it is a density, and we are saying that it is around 0.869 specific gravity. Crude oil is there. Then again click on apply. Then we can go to the viscosity section and we can enter the viscosities of the individual components. So in this, we can also enter the entire viscosity table, like at what temperature, what values are there, and like we can also enter like at different pressures. We can add a new table at another pressure, so we can enter at each pressure at each temperature what the viscosity of the water and what is the viscosity of the dead oil, or we can simply use the correlations, and correlation here is simply like the equation is very simple, like it is AVSK is the it is the viscosity at ambient condition, and then C is the effect like BVSK, you can see the unit is uh, Celsius. So it is basically it's the temperature coefficient, like how the viscosity is changing with temperature. So at this point, we can as we are assuming that the entire entire core flooding experiment is going at a constant temperature. So for this BVST, we will be entering the zero values, and for the AVST, we will be entering the viscosity at the ambient condition. So this value is 0.8177, and for the dead oil, it is 10.94. So if we enter 0 in BVST, it will assume that for entire temperature range, these two components have these particular viscosities. Then click on apply. Now, if we had the gas data, we would also have entered the gas viscosities and the enthalpies of these components. Then in the general section, we have to enter these values, that is what is the reference temperature and pressure for the values which we have given, and what is the surface temperature and surface temperature and pressure. Now we can go on with the default values, but we can also enter the values if we know those. So here the reservoir pressure is taken as 100 kilopascal and temperature is 31 degrees Celsius. The surface condition surface pressure is taken as 150 and the surface condition temperature is taken as 31. So you also remember that these pressure and temperature was also the same values which we have given while specifying the rock properties in the reservoir section. We can click on OK, and then we can click on apply and then click on OK. And we can see that these graphs for the gas, like for gas, we don't have anything. So for oil and water is as is created. So like the water density is increasing with pressure, water viscosity is not increasing and it is constant. Similarly, for oil density, we have taken a constant value, and for oil viscosity also there is a constant value. So these all are the components that is required, and some other components like the surfactant polymer will be added in the later stage. But before that, we have to create a relative permeability data, because that relative permeability data is again used, or you can say it is again used to create a different data after we specify the surfactant or polymer component. So that I will show in the next step. So let's go to the rock fluid section and create the relative permeability data. So this I think like yesterday also the Vishnu sir have told how it is created, and we can simply create. We have to create a new rock type, and this dialog box opens, and we can, if we know the exact data of, or you can, if we know the exact relative permeability data of the score or the whatever reservoir you have, you can enter that, or you can use the correlations, and that is a Core's correlation. So in this experiment also we will be using the Core correlation, and let me just enter these values which I have for this practical. So here also you can see that even though we do not have any gas phase, like we know that there won't be any gas phase during the entire simulation run, but still what we have entered the values for the gas liquid table, because again the reservoir does not, the simulator does not know that there won't be any gas, and it has not been written that for if there is no gas, then different set of equations has to be solved. It will again solve the same equations, and it needs the data, though those data might not be required during the simulation run, but still we have to give these information. And that's why, like for the most of the data that I have given for the that corresponds to the gas liquid table is mostly like 0 or 1, because that won't have much effect on the entire when the result will be coming, because we know that, but the reservoir simulator does not know, and it needs all those data. So I will click on OK, then again I can click on apply and click on OK. So this is the relative permeability data which you can see. This is the oil and water relative permeability data, and this Kr versus saturation of liquid shows the relative permeability data of the liquid and gas table, and this shows the three-phase relative permeability data. So now next thing is that we have to add the initial condition for this model. So I'll go on the initial condition section and double click on this, and this option comes. Now, yesterday I think there was some options was not available for the 2013 version, but I think only one this option has been added in the new 2018 version, but it is not of much importance at this point. Now, As far as I remember, yesterday must have given the uh, reference pressure and the reference depth and the water wall contact and the ballpoint pressure. But since this core is very small, like the entire diameter might be of just 1.5 to 2 uh, 1.5 to 2 feet inch. So the vertical equilibrium or the gravity or the separation of the oil and gas as per the capillary pressure won't be much. So that's why we will be selecting this option, that is do not perform vertical equilibrium condition calculation, and we will select this. But for a very large or very thick reservoir, we mostly go with this first option, that is the depth average capillary gravity method. And because it calculates at different depths what is the saturation, what is the initial saturation of oil and gas. But in this case, when we are selecting this, it will have a same value for all the blocks and for all the depth. Like if we divide this in z direction also, then also if we select this option, it will specify all the blocks in the all the layers in different depths will have same initial oil saturation and initial water saturation, and that initial value will be taken from the relative permeability data that we have given, that this is the connate water saturation and this is the connate gas saturation, or whatever information we have given there, that will be taken when we will select this do not perform vertical equilibrium equation. And I can click on apply and click on OK. So after specifying that the saturation profile is same for the entire grid, and the pressure will also be same, you can see that now this reservoir section has no errors or no warning signs is in this reservoir section, which was earlier present. So that's why we have not taken care about the warning sign at that point, because we were knowing that when we will specify the initial conditions, that pressure difference or that pressure value will be taken care of. So let's save the data set at this point. So let's next go to the numerical section. Click on numerical controls. So here we have to specify some of the things because like because we are doing a core flooding experiment, and like in core flooding usually the entire model or the entire experiment usually runs for maximum of 2 days, and you need the data of every minute or every hour. But whereas in case of the when you go or to do the reservoir simulation, we do not need the data of each and every hour or each and every day. Like every day is like might be there, but again, if you need the data of every day, the entire simulation run will be very long. But so that is why in that case, this, like this, you can see that the minimum time step, it is point 0. It is very small, and here we have to specify this first time step size after dt well. And if we give a very large value, then we won't be able to get the data of every hour or every minute if we want. So for this case, I will select 0.001, and the day automatically is added after I click enter or click on any arrow button. So this is basically because it shows that the first, like whenever there is a change or in the well parameter or any parameter is changing in the simulation, the next time step that will it will be run, it will be run for 0.001 day. And usually this time step is very like it is usually like 1 day or 2 day for a very large reservoir simulators. But for the core flooding, because we need the data, so that is why we had to specify a very low value for uh, this keyword or for this option. other thing is that we have to select this isothermal option as on. By default, it is taken as off, but we will be selecting it as on because because we are assuming that this entire uh, model or entire experiment that will be done is in isothermal condition, and we'll click on apply and click on OK. So you can see now we have also got a green tick in front of the numerical section also. So let's save it again. So till now we have not added any like any surfactant or any polymer or any other chemical that we might be using during the simulation run. So for adding that component, we will be using using the component section. Now, for adding those the surfactant polymer, what we can also do is we can again go on click on this add and edit components, and we can click on this again add and click edit option, and we can manually enter those values. But the CMG also have given a process wizard using which we can enter the properties, and it will automatically create a component for us. So, like for example, just for example, I am showing like if I have a surfactant, so I will add this at surfactant here, and let's say it is surf. I'll click on OK, and because the surfactant will be in aqueous phase, I can click on aqueous. And if I know these critical parameters, pressure, temperature, and molecular weight, I can use those. I can enter those values and then click on apply, and this surfactant parameter will be added. But after adding this, we have to go to like the then we also have to enter the viscosity of that, the density of that, and we have also have to enter the IFP data of that. So this is like a bit lengthy process, but if like you should know that it's also an option. So at present, I won't be using this, and I will be showing how to use the process wizard. So let me just click on cancel, again cancel, and go to this. Like now the process wizard is again in this component arrow button option. I can click on that. Now this window is open where we have the option of choosing the process which we want to implement in this. Like if we want to have a foam flooding, we can click on foamy oil. If we want to have a combustion flooding, we can select this combustion model. If we want to have like alkali, surfactant, foam, and polymer injection, we can select on this. And like other like low salinity water flooding with optional fine migration, asphalt precipitation model. These are models are there which we can use, and we can simply enter the values, and the CMG will create the component for us. And in this section also, like in this 2018 version, I can see that I have 5 options, but maybe in previous versions, I might only get 3 option or 2 options among these, and maybe in few like in the new version, I might see some more options, but I can use these options like to create the surfactant or polymer injection component. So as I will be telling you about surfactant polymer injection, I will click on this alkali surfactant foam and polymer injection, and you can see a lot of data come here. Like for other also, like some description is given. So after selecting alkali surfactant polymer or foam injection, I will click on next. Now this option, like this can vary. The second step which you see will vary depend upon which model you will select. Like if I select let's say low salinity, I'm getting this window. The second step is different. So depending upon the model, the steps of this process wizard can change. So let's again select the polymer injection, the surfactant polymer injection, and click on next. Now here I have the option of selecting different components, like whether I will be doing only polymer flood, or I will be doing alkali and surfactant flood, or I will be doing alkali, surfactant, polymer, all three, or only surfactant flooding will be done, or surfactant polymer will be done, or like other options are like foam flood with gas flood model, foam flood with liquid foam model, and foam flood with empirical. So in this also, like in previous version, you might only see the options for alkali surfactant polymer and foam might not be there. And which is, I think, in 2013 and 15, the foam flood option was not in this model selection option. So for this, I will select the surfactant polymer flood and I will add the two components. So after selecting this model, these different options are there, among which I have to enter the values which is required. So first options, if you can see from the top, is like is the polymer viscosity a function of salinity, and which we know mostly is, but maybe for this experiment we might not have that data, so we can leave this unchecked, or we can check this option if we want to enter the polymer viscosity as a function of salinity, like and if is the polymer getting absorbed on the reservoir rock. So maybe we have not done the adsorption study for the polymer and we might not be having that data, so in that case we will uncheck this, and but for this maybe we will keep this as checked. And other options like polymer resistance factor, we are assuming it to be 5, or 1 you can see it is showing that 1 is for no permeability blockage, and accessible pore volume, the polymer quality, whether it decreases with time or not. And so if it decreases with time, then what is the half-life of that polymer? So these are the options that is the simulator is asking specific to the polymer. And then these next options are related to the surfactant flooding, like if the surfactant is partitioning into oil or not, and if the surfactant is having reversible partitioning of surfactant from the oil. So this basically means that is like when the surfactant basically reduces the IFT by getting absorbed at the oil and water interface, but at higher concentration it can also enter into oil phase. So whether it is entering into oil phase and if there is a reversible partitioning or not. So if we have that data, then we can, if we know that that is happening, we can select or keep that unchecked. If we do not assume that the thing, then next important thing is how many relative permittivity sets will be used for the interpolation. And this is like the very important part of a surfactant flooding. And we have entered uh, one relative permittivity data, and what basically the surfactant flooding does is due to the reduction in IFT, it alters the relative permeability data, and how it alters is that it allows for the ease of relative permeability data is basically like when two phases are present, one of the phase is having difficulty in moving from one part to of the from one pole to the another. But when the surfactant is adding, that it becomes easier for that components to flow. So that's why we need to create a different sets of relative permeability data, so that that will be used when the surfactant is flooded. And if the surfactant is not flooded, then the basic or the the initial relative permeability data is being used. So in this case, we will be using three sets of relative probability data, and one of these three sets will is usually the data which we have already given, and that is why we have given the raw fluid data before entering into this process wizard option. And the second relative probability data is usually a straight line, where it is assumed that if there is like very less or no interfacial tension between the two phases, the two phases will be easily passing through the pores, and it will be a straight line. And the third is just you can say interpolated between these two extremes. So let me just show you that how it is there. Like let's assume. So let's assume let's assume this was the initial relative permittivity data which we have given. The the one of the three interpolation sets will be this one, that this is a straight line, and this is assumed for like very low or no IFT between, like no interfacial tension between the two phases, or you can say for miscible flooding, this will be the uh, this in, relative permittivity data will be used, and the third interpolated will be somewhere in between these two uh, sets. So these three interpolation sets will be created by the CMG, in which two are usually these two, and the third is a interpolated one. So for that also we have the different options of like specifying how much acid residual oil saturation might be changing, how much the relative permittivity data will be changing, and these four options, salinity which was there. Yeah, so these different sanity parameter values we will be giving for the adsorption to show how the surfactant and polymer adsorption is there. Then what like which rock we have used for the adsorption study, whether we have used a sandstone or limestone or dolomite. So for that we can select, like if we have used sandstone, we can select that, and we can enter the rock density of that rock, and these all are used to to model how much how much of the surfactant is getting adsorbed when it is being injected into the core, or when it is being injected into the reservoir. Then we can also select the geochemistry modeling, or and we also have the option of selecting whether the salinity is having the effect on IFT or not, and we can tick if we have tested the effect of salinity on IFT, or we can leave it unchecked if we have not tested, or maybe like in this experiment we have assumed that the salinity will be constant, then we will not select this. So these all like options are there which we have to select, and if we have the data we can enter that, and if we do not have the data we might skip these steps. So let's keep most of these data at their default values and move to the next step. So next is this also is this data is all is related to the geochemistry of the fluid, like what is the salt concentration, and like if there is any reaction between the surfactant and the rocks, and that we can enter here, and like for that like we can select what type of reaction might be having, like if the sandstone is having an ion exchange, or the carbonate is having an ion exchange reaction between the injected fluid and the rocks, then we can select this, and like these all options are there to show what kind of reaction might be occurring in the reservoir. And this geochemistry data input, or the this uh, this step 3 is also is has been introduced in this from this 2018 version. The earlier versions we do not have to enter these values, and like uh, those values were not taken into consideration in the previous versions. So let's input the initial salt concentration in terms of Na plus and Cl minus ions as 300 ppm, and click on next. And we are like we have not selected any reaction, so we are saying that there won't be any reaction between the injected fluid and the reservoir rock or the core rock. But if we had the data, we would have entered here, and click on next. Then it says that it has taken all the values, or it has taken all the options, asked for all the options from the user, and then it is saying that whether we have to create a new component for surfactant or polymer. And for this I have selected that yes, we have to select we have to create a new component. And if we have made a surfactant component before using this process wizard, as I was showing just a time before, that name would have come here, that whether we want to use that component or we again want to create a new component. So for this, we have to create a new component because we do not have any surfactant polymer component already created. So, okay, why three sanitides are present? Okay, see, three sanitides are present, like I have shown. Instead of having three sanitides, we can also enter two salinities or four sanitides, but we can only keep one value, and that was because like the salinity changes the how much the surfactant or polymer will get absorbed. Okay, so let's say when no salt is present, a particular amount of polymer is getting absorbed on the rock. But when we increase the salinity, what happens is the the amount of polymer that will get absorbed on the rock will increase. So if we have that data, like if we have tested for let's say five salinities and we have found five different values for that absorption, or and then we will be using different salinity values in that step. Okay, is it clear? Okay, see, okay, let me show you this. Okay, let's say when we, like in aqueous phase, we do not have any salt ions, we only have polymer present. So what happens is, let's say we have, yeah, okay, let's say we have a polymer in the injected fluid and we have polymer in the, wait, mm, in the produced fluid. Now, what happens is, and let's take here salinity. And when we do not have any salt ions, that will be like zero salinity is there, and we are injecting, let's say, 500 ppm of polymer. But when the entire polymer solution is passed through the core or through the reservoir, some of that polymer gets absorbed on the rock surface, and in the produced fluid, we might only be getting, let's say, 300 ppm of the polymer. So 200 ppm of polymer is getting adsorbed. Okay, so this is the amount of adsorb. But when salt ions are present, let's say like 1000 ppm of NaCl is there, and again we inject 500 ppm of polymer, what will happen? This amount of polymer that is getting adsorbed, this will increase, and it might happen that only we are getting 200 uh, ppm of polymer in the produced water. So in this case, it is increasing, and usually it increases. Like when the salinity is increased, the amount of adsorption of surfactant. Okay, I understand the term. Okay, see, that's what I'm going to tell. And it is not that the like you might be thinking why multiple sanities, and multiple sanities is because it's not a linear curve that okay, if we increase from 100 from 0 to 1000, like 100 ppm is increasing, and if again I increase it from 100 from 1000 to 2000, if we can, you are assuming that it will be 400 ppm. But this relation, which I'm showing as a linear relation, this may not always be true. It might happen like at 2000, like at 2000 ppm. Again, if I'm injecting 500, only 150 is there. So this, for that, it will be 350, right? So this uh, adsorption relation to increase in the salinity is not always linear, and that's why we might need different salinity values, and we might have to enter different adsorption values at different salinities. Okay, is it clear? Because the effect of salinity is not linear. Yeah, okay. Okay, so I will be clicking on this next option, and I will create this will create uh, like two components, and this again I have to select which rock fluid property I will be using for the interpolation and creation of the interpolation sets. Then click on next. So here I can enter the the interfacial tension data for the different surfactant concentrations, and the CMG already provides a reference, or you can say some default values, but obviously depending upon our lab results we can change this data, and let's keep this data for this experiment. But usually we will be having a different set of data for this, like what is the IFT, a different weight percent of surfactant. Then click on next. Now we have to select the we have to select what is the different adsorption values for the different salinities, and here again like uh, we have the different default values which is provided by the CMG, but when we will be having these data we can enter these values, and we can tell the simulator what are the different amount of surfactant, different adsorption of surfactant polymer at different salinities. So this is the surfactant adsorption data, and this below is the polymer adsorption data. So I can click on next. Next, we have to give uh, the viscosity data, and here we have we can select give like this default values which you can see is basically the change in the viscosity with the change in the amount of polymer. But let's say we have the viscosity as a function of velocity, or we have the viscosity as a function of shear rate. So we can select on that shear rate and enter the shear rate versus the versus the viscosity data for all the polymer concentrations. So we can change these values, like if we have, let's say we have the data for only three values, like 3 weight percent, 4 weight percent. So we can change that, and we can enter the shear rate from which the for which we have tested the data. Sorry. So we can enter all these values, or we can enter in terms of the velocity, and we can keep that whether, let's say we do not have that data, we only have the simple viscosity data at a single shear state, then we can enter these values. Also, we can enter the temperature dependent viscosity of the polymer solution. So at this point, let's keep for only one of the, for, because we are assuming that the entire process is going to be isothermal. So these are the values which we will be selecting. So here you can see that by default for 0 weight percent it has taken the value of 0.8177. That was the viscosity of water which we have given when we have uh, made the component of water, and this highest value it has taken from the oil data, but we can change these data if we have the exact data. So for time being, again let's keep this as given as the default values, and click on next. Now in this case, this step we have to select which wells will be using, and for which well how much will be the injection data. But this is at present entirely blank because we have not yet made any, we have not specified any wells. So this also we can, there is nothing to tell here. But if we have the injector, we have all, let's say we are moving from a stars model, from an IMS model to a stars model. So for that star IMS model we already be having some of the injector wells and the producer wells. So from that list of the wells we will be selecting the particular injector wells, and we will be selecting at which date what surfactant and what polymer concentration will be injecting in that wells, and that we can do from this step 9. Then after clicking finish, it will automatically incorporate the well information in the well section. So at present, since we do not have any wells, we can simply click on finish. Okay, so now this this creating the components is over, and now you can see, like earlier we only had the H2O and the dead oil. Now we have the surfactant polymer and the NaCl components also created. So I think I will start from this in the next session, which is at 11 a.m. And let's take a break at this point. And before that, let's also save this data set. Okay, so we will meet at 11 a.m.